Hello, I'm Yuya Tsuda from Kyoto University, Japan. I'm going to talk about space-efficient gradual typing in Coercion-Passing Style. Gradual typing combines static and dynamic typing within single programming language to obtain advantage of both approaches. Gradual typing enables code evolution from dynamically typed prototyping code to statically typed production-level code. Let's consider this gradual type program. This example program shows well-known functions that compute given number n is even or odd by mutual tail recursion. This program is expected to run efficiently thanks to tail call optimization. However, this definition is different from the normal one in one point, that is, the return type of even is annotated by this star symbol. This star symbol is called the dynamic type, and it means this part is dynamically type checked. Thus, even is partially dynamically typed function, while odd is statically typed function. In gradual typing, statically typed function and dynamically typed function might be mixed like this. What happens if we compile this program in an existing gradual typing compiler? In fact, if input number n is very large, it results in stack overflow in recently developed compiler called Glyph. It means that naive implementation of gradual typing would fail to optimize this kind of tail calls. On the other hand, our modified Glyph compiler successfully computes this program thanks to tail call optimization, even if n is very large. This is one of the main results in this work. So what kind of modification did we make to Glyph compiler? In fact, we implemented an additional translation path into what we call Coercion-Passing Style. Here is a brief overview of this study. We investigated Coercion-Passing Style as an implementation technique of space-efficient gradual typing. Our main contribution is formalization of Coercion-Passing Style. We defined formal translation into Coercion-Passing Style as a translation from Siek et al.'s lambda s to new calculus lambda s1 with first-class coercions. We proved correctness of this translation. Then we also implemented this translation on top of a Glyph compiler, as I have already mentioned. Next, I will try to explain key ideas of Coercion-Passing Style. Before that, I should explain more about the problem we want to address in this work. Compilers of gradually typed language first insert runtime type checks into user programs. In this case, runtime checks are inserted like this because of the mismatch of return types. First, we need tagging coercion blue band. This blue part has the Boolean type, but the return type of is even is the dynamic type. So we need coercion from the Boolean type to the dynamic type. Likewise, we need tag checking quotient bool question from the dynamic type to the Boolean type here. Here, angle brackets are used for Coercion applications. The problem is Coercion applications inserted at tail positions like tail recursion. We can rewrite such a program in tail recursive forms by the idea of Coercion-Passing Style. In Coercion-Passing Style, every function takes an additional coercion parameter that will be applied to the return value. These additional coercion parameters are similar to the accumulated parameters added to make programs tail recursive in functional languages. We combine Coercion-Passing Style with prior theoretical work on the problem called space-efficient gradual typing. We use Siek&Taha's coercion composition operation to collapse coercions eagerly. I will explain key ideas of Coercion-Passing Style by using even-odd program. As I have already said, this tail recursion was broken by coercion insertion. If we rewrite this program in Coercion-Passing Style, we'll get this program. Even-odd functions take an additional coercion parameter, C or D, that will eventually be applied to the return values of functions. Function call followed by coercion application is replaced by one function call. We compose coercion bool bound and the accumulated coercion C, and then pass the composed coercion to the function. Composition is denoted by open semicolon. Before returning a value, we apply the accumulated coercion, which is denoted by angle brackets. As you can see, coercions are used as first-class values. In Coercion-Passing Style, even-odd functions become tail recursive again. This is the most important thing. Next, I'd like to talk about formalization of Coercion-Passing Style. We formalize new calculus lambda S1 for Coercion-Passing Style. As I have already mentioned in even-odd example, coercions are first-class values in lambda S1, unlike other coercion calculi. Lambda S1 has special constructors for functions in Coercion-Passing Style. Function takes in additional coercion parameter k. We also need to pass additional coercion argument to a function. We also need types for functions in Coercion-Passing Style, AOOB, and corresponding function coercions, COOD. I want to explain the intuition of type AOOB in the next slide. To do so, let's look at type annotations for even-odd functions in Coercion-Passing Style. This is type annotated version of even-odd functions. This curved arrow means coercion type. Since coercion C will be eventually applied to return value of even, if continuation coercion C is from the dynamic type to type X, then the return type of even would also be X. Such type X would depend on coercion that will be passed to even function. We need such polymorphism for functions in coercion-passing style. In general, functions in coercion-passing style have this form of polymorphic type. It is written A-B in our formalization. We formalized translation into coercion-passing style as a translation from Siek et al.'s lambda s to our new calculus lambda s1. These are a few examples from term translation. The first example is the translation of identity function. Here I wrote k for additional coercion parameter. Then in the second example, function application followed by coercion application will be merged into single function application. We need to prove correctness of the translation. We prove correspondence between behaviors of M and translation of M. This correspondence is straightforwardly proved by the simulation property. One-step evaluation in source calculus corresponds to multi-step evaluation in the target calculus. I don't have enough time to explain details, but we had to carefully set definition of translation for this simulation property to hold. Then I'll introduce related work. There have been some theoretical work on space-efficient gradual typing. Herman et al. First observed space efficiency problem in gradual typing, and they gave its solution by eagerly collapsing consecutive coercions. Afterwards, Siek et al. Studied space-efficient coercion calculus lambda s. This work improved Herman's work by coercion composition. We use this calculus as source of our translation. However, implementation of these calculi were not very trivial. These two papers studied implementation of space-efficient gradual typing. They both directly implement space-efficient gradual typing. Their approaches are different from ours. Our approach by inserting another translation path can be merged into existing compilers. This is a summary of this presentation. We studied coercion-passing style as an implementation technique for space-efficient gradual typing, particularly focusing on tail calls. We formalized coercion-passing style translation as well as target calculus lambda s1. Lambda s1 has first-class coercions. We also implemented the translation on top of the glyph compiler. In the paper, we have full definition of coercion-passing translation as well as target calculus lambda S1. We also have correctness proof of the translation. Actually, we found that naive translation definition breaks the simulation property. To fix this, we had to define translation by a mutual recursive definition. We also conducted benchmark experiment and compared running time in our modified compiler with a modified original glyph. We confirmed our modification works for practical programs with some overhead. Thank you for your attention.